On November 5, 2025, astronomers captured a post-perihelion image of interstellar visitor 3I Atlas, revealing a compact coma with no visible tail, defying expectations set by solar encounters. If even our best telescopes find no clear evidence of comet-like activity, what does this mean for everything we thought we understood about these rare cosmic travelers? The answers begin with tonight's unprecedented update. 3I Atlas first drew attention in July 2025, when the Atlas survey in Chile detected its hyperbolic path through the solar system. Unlike the parabolic or elliptical orbits of most comets, its trajectory, eccentricity greater than 1, confirmed an interstellar origin, joining only two previous objects of this kind, Oumuamua and Borisov. As 3I Atlas approached perihelion on October 21st, researchers mobilized major telescopes to capture its behavior. The Hubble Space Telescope measured a nucleus diameter likely under 1 kilometer, with estimates ranging from 0.32 to 5.6 kilometers. Meanwhile, the James Webb Space Telescope revealed a composition rich in carbon dioxide, with far less water ice and water vapor than typical solar system comets, and traces of carbon monoxide and carbonyl sulfide. Early images from the Very Large Telescope and European Space Agency Mars probes showed a diffuse, reddish coma and emission of cyanide and nickel vapor, suggesting active outgassing. These findings set expectations for continued activity after perihelion, prompting a focused search for changes as 3I Atlas moved away from the Sun. On November 5, 2025, a new image of 3I Atlas was published by an observer at cometas.sites.net. This frame, now widely referenced in scientific discussions, captures the interstellar object after its closest approach to the Sun. The most notable feature is a compact coma, nearly point-like, surrounding the nucleus. No clear comet-like tail is visible above the image's detection threshold. The observer's work has been cited in a technical commentary by Loeb. His article discusses the absence of a resolved tail as a significant result. Further analysis is available in Loeb's November update at avi-loeb.medium.com. This single frame serves as the basis for current scrutiny, anchoring the investigation on verifiable, time-stamped data. The observer's technical note, addressed in the next segment, will provide additional context for interpreting these findings. This is the technical summary for the November 5, 2025 image of 3I Atlas. The observer provided a concise account of image acquisition and processing steps. The final frame was produced by stacking 10 individual exposures, each lasting 300 seconds, through a broadband R filter. The telescope plate scale was 0.5 arcseconds per pixel, providing fine sampling of the compact coma. To reduce noise and enhance faint structures, the images underwent median subtraction and deconvolution prior to stacking. The observer noted that the processed image was released as an 8-bit PNG file, while a request for the original FITS files and full metadata remains pending. The written summary specifies no tail was detected above the 3 sigma surface brightness threshold, but it does not assign a quantitative value to the detection limit or to tail length. These technical details establish the observational context and serve as the foundation for any further quantitative analysis of 3I Atlas post-perihelion activity. Detection limits. Quantitative limits define what the November 5, 2025 image of 3I Atlas can and cannot reveal. According to Dr. Marco Micheli, a photometry and point spread function specialist at the European Space Agency's Near-Earth Objects Coordination Center, the 3 sigma surface brightness floor for this setup is about 27.5 magnitudes per square arc second. This means any tail feature would need to be brighter than this limit and extend at least 10 arc seconds from the nucleus to be detected. Tails fainter or shorter than these thresholds remain invisible in the data. Achieving deeper sensitivity, down to 28 or even 29 magnitudes per square arc second, would require longer exposures or larger telescopes. For now, the current frame establishes a concrete observational boundary. No tail meeting or exceeding these criteria is present. The next step is to consider how different physical scenarios might produce a tail below this detection floor, or none at all, given these constraints. 5 scenarios remain consistent with the November 5 image of 3I Atlas. First, a sharp drop in dust output after perihelion, possibly caused by rapid loss of near-surface volatiles. In this case, only a small amount of large, slow-moving grains would linger near the nucleus, producing a compact coma with no extended tail. Second, a grain size distribution dominated by particles too large for solar radiation pressure to sweep into a visible tail. Third, viewing geometry effects. If the dust tail aligns closely with our line of sight, its surface brightness could fall below the detection threshold. Fourth, fragmentation into sub-resolution debris is also plausible, leaving only a faint, unresolved haze. Finally, the coma may reflect a combination of these factors, with both low ongoing activity and unfavorable projection. Professor Karen Meach notes that multi-epoch photometry and spectroscopy will be essential to distinguish among these possibilities. Misconceptions often arise from the absence of a clear tail in recent images of 3I Atlas. A compact coma in an image does not imply the object is inactive or non-cometary. Large dust grains or low-level outgassing can produce a compact appearance, especially if most dust remains close to the nucleus. A single image cannot rule out faint or short tails that fall below the detection threshold. Deep, repeated imaging is required to separate transient features from background noise and to detect low-surface brightness structures. Known cometary processes explain the observed features. Current data do not support claims of an artificial origin or new physics. The morphology we see is consistent with dust grain size distributions, viewing geometry, and reduced activity after perihelion. Coordinated follow-up is essential. Observers are encouraged to obtain long-exposure broadband R and I images, use narrowband CN and C2 filters, and to gather spectroscopy when possible. Sharing raw FITS files and associated metadata with the community will enable independent verification and deeper analysis. Collaborative efforts between amateur and professional observers, combined with open data exchange and careful, repeated observations, remain the best path to resolving outstanding questions about 3I Atlas. Confirmed. On November 5, 2025, the only confirmed post-perihelion image of 3I Atlas showed a compact coma with no resolved comet-like tail. This observation, credited to cometas.sites.net and analyzed by Loeb, established a surface brightness detection limit of 27.5 magnitudes per square arc-second, confirming that any tail longer than 10 arc-seconds would have been visible. Limits. Despite extensive scrutiny, the raw FITS files and full observer logs remain unavailable, leaving some technical details open. Experts have outlined 5 plausible scenarios consistent with the image, including low dust output and possible changes in the object's activity after solar passage. The absence of a visible tail challenges standard expectations for interstellar comets and highlights the need for deeper imaging and raw data sharing. Definitive. As of this update, no further post-perihelion images have been released. The November 5th frame stands as the definitive record, marking both the progress and the limits of current knowledge about 3I Atlas.